So welcome to lesson 2. Lesson 1 we looked at exponentials, we looked at how to sketch them, we looked at transformations of exponentials, and we looked at some examples of that. And in some ways we're going to do very similar with logarithms. They are the partners of exponentials, and we're going to look at how they are in partnership. So first of all, logarithms came about in about 1612, 1613 by a Scotsman called Napier, who brought the two words logo and ethnium together, the logic of numbers. I think he was in collaboration with a European, and they came together. Did they discover it? Did they invent it? Who knows? But he brought it about. He had a problem. He needed to solve it. It was a complicated problem to solve. He wanted a quicker way to do it. This video gives a picture of how he did it. And you can see if you can get all the way through that video. So let's quickly look what we did. As I said, we looked at sketching, we looked at transformations, we did all of that sort of stuff. And now we're looking at logs and their laws. So let's look at discussion point. Let's consider, and I'll let you think about this for a second. In an experiment, the number of bacteria present, n, after t hours is given by n equals 2 to the power of t. How many complete hours is the number of bacteria greater than 1,000? So, here's the problem. How are we going to solve it? Now, if you were given this problem in GCSE or in year 10, you'd probably try and solve it using trial and error and develop that to trial and improvement. But that's kind of laborious and slow. Yes, they want complete hours, and you could click, 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 click and do it that way, but it could take some time. So let's think of it a different way. Let's consider a different way. If I asked you x squared equals 40, what's the value of x? You will instantly tell me to find the square root of 40. That is, you will find the inverse operation in order to solve that. So we need to know what is the inverse operation of the exponential function. Drum roll, brum, bum, bum, surprise, surprise, it's logarithms. Let's think about this first. Let's look at the exponential. When we have an exponential like 2 to t, the base is 2 and t is the power, and that's what we call it. So base 2 to the power of t. And we need to rearrange this to get t on its own. Now, just as you can write a number as an exponential, you can also write a number as a logarithm. And this rule here is really important for you to know. So you need to know this one, copy it out and really understand it. This fun video here is a really nice way of showing it. So I would look at that. So let's consider the number 64. 64 is 2 to the power of what? So you can write 64 as 2 to the power of what? And you should know it's 2 to the power of 6. So therefore, I can say that 2 to the power of 6 is 64. I can rearrange that using log terms and say that it's log base 2 of 64 is 6. A half I can write as 2 to the minus 1, so the power is minus 1. And therefore it's log base 2 of a half equals minus 1. 1, and a unique number, the Romans didn't think it was a number, I believe, but you can write 1 in a myriad number of ways. For instance, 2 to the power of 0. Hey, presto. 2 to the power of 0. The power is 0, base is 2. So log base 2 of 1 is 0. In fact, the log base of any number of 1 is always going to be 0. Now let's consider the square root of 2. Don't forget, the square root of 2 can be written as 2 to the power of a half, the power being a half. So this can be written as 2 base 2, base 2 of root 2 equals a half. Too many 2's in that one. So get used to how to rearrange it and swap it between the exponential and the log. Get used to that, practice that. Again, as I said, that video is a nice way of learning how to do that. So let's go back to the question. Here we want to find out the value of t such that 2 to the power of t is 1,000. So I can now say the power is t, the base is 2. So log base 2 of 1,000 equals t. And on my calculator, I've got a button there. I just have to click that button, put in the base, put in the 1,000, press the equals button. You do it on your graphic calculator as well, and you get an answer. Now they just want an answer of 10. But if we want to be more accurate, more precise, there is a fantastic button there, which I haven't used until I was later in life, and that gives me the hours, minutes and seconds. And so by just clicking onto that after I've got this answer, gives me that it's 9 hours, 57 minutes and 56.82 seconds. Now let's consider, firstly, most of the work we do with logarithms is written in two forms. One, the natural log, and we'll look at that later. The other is base 10. And it's so widely used that your calculator has a button devoted just for that. So base 10 is a very common one. We deal in the decimal system, decimal place. So that's kind of an obvious one, and we often use it in day to day. But obviously with calculators and computers, it's base 2. So you do need to understand different bases. But for day to day, it's base 10. You also need to know about the laws of logarithms, and you need to know these off by heart, and they follow the same as those for indices. And so I've just copied these out from that book. Copy these out yourselves, go through them, practice them, try them out. For instance, log of 1,000, if you want to write 1,000 as 10 times 100, then log of 1,000 should be the same as log of 10 plus the log of 100. Try it out on your calculator, see if you're right. So try these. Again, notice the logarithm of 1 is 0, always the case. And right at the bottom, the log of its own base is also 1 here. So really quite nice. Learn these ones and they'll help you. I like the one there, log x to the power of n can be written as n log x. Use that one a heck of a lot. I guess in time, by practice, you will forget to have to learn it. It will just become second nature. Let's have a couple of examples. So firstly, write 3 log p plus n log q minus 4 log r as a single logarithm. So in this we want a single log. Notice they haven't got their bases. That's because it is generally accepted that this will be base 10. You don't have to convert the bases. You can do that. I'll teach you about that later. But here they've all got the same base, so we don't have to worry about that. But what we do need to do is get the 3, the n and the 4 out from being in front there. So to do that, look back at those laws again. Said we use this one here, really kind of neat one, and that's the one we often use here. And we can convert that to log p to the power of 3 plus log q to the power of n minus log or r to the power of 4. Once we've done that, we can now go to the two other rules that we use, the multiplication and division ones. Look at these ones. So we look at the additional one, means we multiply these together, and subtraction means that that gets divided by the product of these two, and we end up with a fraction. I'm going quite fast, but you can look at these, take it down, copy it, etc. This one here, we want to express this huge log and split it up now in the other direction. So we want to divide this into the 3 component parts. As you can see, it's just timesing becomes adding. So there's the 2 additional points here. The 2 that will drop down. This you can write as r to the power of a half, and that drops there, and you get this long expression. Let's look at example 2. It says here, given that log y equals all of this, express y in terms of x. Notice no express log y or anything like that. It's just simple, what is y in terms of x? So what we've got to do is got to tidy this up. It's all a bit messy. So things, you can do it in different orders, but the easiest thing is to deal with that one first. So make that go up to the top there, and that becomes 9, log 9. And then you've got the additional there that makes you multiply these two. So we end up with this, and that's a common factor of log comes out, and that's taken out. And now what you get is log y equals log this bracket. So therefore y equals this bracket. And you've now written it y in terms of x. Again, copy this out, take your time. I'm rushing through it, but you copy down and just spend time working through this. Lastly, in this section, we're looking at how to graph logs. Now, as we said right at the beginning, logs are the inverse operation of exponentials. And like a lot of stuff, because it's the inverse one, it's reflected in the y equals x line. So if you're very competent at drawing the exponential graphs, then you simply reflect them in the y equals x when you're doing the log ones. Notice the log ones, your asymptotic line is the y-axis. Notice that it doesn't go through 0, 1 now, but 1, 0. So they're the common features that you should find when you're drawing log graphs. And then the transformations of that operate in the very same way as they would with the exponentials. So what I'd like to do is go to exercise 13.3. You can do 13.2 as well if you want. Try a few of those things, check out the answers, and come back to me if there's any problems you want me to go through. Thanks for listening.